Right, hello everybody. We are still working through our new predicate rules, and next up, we've already knocked out universal out, existential in, existential out. Now we're going to do what's called universal derivation. So let's go ahead and talk about this one. So here's the bad news. There's no inference rule we call universal in, and that might seem sort of odd. After all, we've got universal out, right? We've got existential out and we've got existential in. Why not universal in? We don't have an inference rule like that. Instead, what we have is a new derivation technique. So this is a new way to cancel show lines. So just like DD, CD, and ID all tell us how to cancel a show line of a certain form, UD, universal derivation, is going to tell us how to cancel a show line that has as its main connective a universal quantifier. And so this is going to be sort of similar to the situation we find ourselves in with sentential when it comes to if-then. If you look back at the rules, you'll notice there's no arrow in rule. There's no if-then in rule. Instead, if you want to establish that something with an arrow is true, you have to write a show line with the arrow and then apply the conditional derivation technique. That is, you assume the antecedent and try to show the consequent. Something similar, or at least the rule universal derivation is very analogous to this. No universal in rule, no rule like this, just like there's no arrow in rule. Instead, a new technique, UD, just like there's a technique, CD. That's the basic idea here. UD, that is going to show us or tell us how we cancel a show line of this form. And remember, once we've canceled a show line of that form, we've established that this formula is true. So it's going to essentially show us how to establish as true universally quantified formulas. That's the idea. Okay. Let's think a little more sort of philosophically, if you will, before we get into the nuts and bolts of how this works, how you might go about showing that a universally quantified statement, like the one up there on the slides, is true. That is, suppose you want to show that everything is f. How do you show that everything is f? Here's a few ideas. You could start by just listing everything and checking if it were f. So you see, this pen has property f, and this chalk has property f, right? And this pen has property f, and you just keep going. But if you really think about it, that's not really going to work to show that literally everything has property f. For one thing, it would take too long, right? You can't go through every single item in the universe and see if it has property f. Even more than this, even if you could, you wouldn't sort of know when you'd reach the last object in a universe. So even if you indeed have checked every f, suppose you've got a small domain, and you've really checked that everything in your domain has property f, you might not know whether or not you've reached the last object in your domain. And so for that reason, this sort of listing and checking isn't going to work to show that everything has property f. Here's a more promising way to do it. Suppose you pick an arbitrary new name, so like a new constant, a name you've never heard before. Like, for the sake of argument here, we'll just say alpha. So you don't know anyone called alpha, you don't know any object called alpha, you have no idea what alpha is, you just invented the name. Suppose that even though you just invented the name alpha, you were still able to prove that alpha had property f. That would suggest that there's something special about property f that allows you to prove that some arbitrary individual you know nothing about, alpha, has property f. Not only is there something special about f, it suggests that since you just invented the name, it couldn't be any features particular to alpha, whatever it happens to be, that allowed you to prove that it has property f. It must be something more general. It must be that anything really could be proven to have property f if you could prove of some arbitrary alpha that it had property f. But let's say that again. That means, in principle, it didn't matter which name you chose. You could have chosen any name, anything at all. You could have shown had property f. And that just sounds like a way to show that the universally quantified formula is true. That is, that everything has property f. Put simply, if you can show that f is had by an arbitrary individual about which you know nothing, then it's nothing about the individual itself that allowed you to prove that. It's something about the nature of the property f itself. And that means everything must in principle have that property. This is a little bit more of an abstract sort of idea, maybe a little bit more difficult to follow than some of the other things in this set of lectures. So you might want to think about that a little bit and see if you can sort of get yourself in the mindset where you understand what's going on this slide. Because what we're going to do formally is try to set something up that mimics what's going on over here on the slide. Okay, here's what universal derivation says. In order to show that a universal formula of that form, this form here, is true, it's sufficient to show a substitution instance of that argument, or sorry, of that formula, where C is a new name. Now again, these are a little bit hard to follow with the C's and the V's. It's not the most intuitive way to put it. Let me give an example, and then in the next set of videos, or the next video, I'll go through a couple more example problems like we have. So here's the basic idea. Suppose you've got premise 1 is that all f's are g's, and premise 2 is that everything is f. And you want to show that therefore everything is g. The way we do this is we set it up as what's called a universal derivation. And we say, look, it's sufficient to show that everything is g if you can show that a is g, where a is a new name, a new constant. That is, a is an arbitrary sort of placeholder. And so essentially, if you can complete this proof, we'll say that if you can show from these premises that a has property g, well, you could have shown for any individual, no matter what name you chose there, B, C, D, E, that it was g. And that's enough to show that everything has property g, given these premises. Okay, that's the basic idea. I hope it makes some sense. Maybe it will make a little bit more sense as we do some example problems. Those are on the next slide here, and I'll make a new video for that going through these examples.